Okay, so this unit 5 deals with two types of functions, exponential and logarithmic functions. That image is it's a picture of something called the slide rule, which is a calculator that was invented in the 1600s. And believe it or not, other than graphing, you can do any calculations on that slide rule that you could do with a graphing calculator. You can find sine, cosine, tangent, cube roots, 11th roots. You can raise numbers to any power that you want, decimal or fractional, and it works by taking that middle piece and sliding it around. And it uses something called a logarithm, and that's why I have that image. If you were to take a look on the front cover of this handout and read, I'm not going to go through each of these individually, but read all of the objectives, you'll find a recurring theme throughout this unit. There's a lot of talk of exponential functions. And there is a lot of talk about exponential equations. There is also a lot of talk about logarithmic functions and logarithmic equations. So this whole unit deals with two types of functions and equations, exponential and logarithmic. And today what we're looking at on page 1 is exponential functions, just a basic introduction. So what is an exponential function? An exponential function is any function that can be written as y equals some number raised to an x. Now there's going to be variations of that definition, because if I take an exponential function like y equals 2 to the x, I can transform it and make it look more complicated than just having a number raised to the x. But this is the starting point. If you take a look at what it says here about the base has to be greater than 0. So what does that mean? It means the base cannot be 0 and it cannot be negative. It must be a number greater than 0, but it also says that the base cannot be 1. And there's a graphic that I came up with here that I think really illustrates what C is allowed to be. And I would like you to take a second and reproduce that graphic, or take a picture, whatever you want. The arrow represents all of the values that the base in an exponential function can take on, but it cannot be 0 and it cannot be 1. There are reasons for that I don't think we need to really get into right now. The basic idea is if the base is 0, then the function just becomes y equals 0. And if the base is 1, it doesn't matter what x is, y is always going to be 1. And those are not considered exponential functions. Those are degree 0 polynomial functions. And we're going to come back to this diagram multiple times. So examples of exponential functions that fall into this category are y equals, or f of x equals 1.35x, y raised to the x, y equals 2 raised to the x, n as a function of t equals 1/2 raised to the t. So the basic idea is we have a number raised to a variable. First example asks us to graph these exponential functions, and we're not going to graph them on a graphing calculator because we need to use this example to teach us about exponential functions and how they behave. And then we're asked for all these properties. So to begin with, I'm going to do this with a table of values. Y is found by taking 4 to the x. So if I were to take, I'll use x equals 1 to begin with. If I were to take 4 raised to the 1, I get 4. That's pretty clear that when x is 1, this function, when x is 1, ends up giving us y equals 4 to the 1, which is 4. When x is 2, we're going to have 4 to the 2, which is 16. And I want everybody to pay careful attention to the fact that when x goes up by 1, y gets multiplied by 4. And 4 is the base in the exponential function. And what I am going to end up calling that base, starting now actually, that base is the factor by which y gets multiplied by regularly. If we were to put x equals 0 in, you would have 4 to the 0. Well, we know the definition of 4 to the 0 is 1. And you can see that As x goes from 0 to 1, which is an increase of 1, y gets multiplied by 4. If you were to put in 4 to the negative 1, you should know that 4 to the negative 1 means 1 over 4 to the positive 1, which is a quarter. I suppose you could use your calculator, but this is a quarter. And I want you to notice again, as x goes up by 1, y gets multiplied by 4. In other words, everybody, if you move 1 forward x-wise, you multiply y by 4, but that must mean if you move 1 backwards x-wise, you divide by 4. So I could take this 1 quarter and divide by 4 and get 1/16, which is 4 to the negative 2. I think it's very, very important for you to understand that you're multiplying regularly by some number, and that number happens to be 4. Then when you construct this graph, it kind of makes sense as to what you're going to do. I want to start off with the idea that when x is 0, y is 1. So we have a data point or a mathematical point at 0, 1. When x goes up by 1, which means we go from 0 over to 1, y gets multiplied by 4. So now it's 4. Can somebody type in the chat, please? Is the grid scaled on your handout the exact same way it's scaled on the image you're looking at? Okay. So now when we go over another 1, y, which was 4, gets multiplied by 4, which gives us 16. When we go back 1, y was 1, it gets divided by 4, so it becomes a quarter. And I'm not going to try to graph negative 2 comma 1/16. But I want you to understand something that's fairly important with exponential functions. If I were to continue to go backwards and divide by 4 each time, actually, you know what I will do? I will indicate it with an arrow. If I were to go back another 1, it would be at 1/16. If I were to go back another 1, it would be at 1, my goodness, 64th. If I were to go back another 1, it would be at 1, I think, 256th. I hope you appreciate no matter how far I go to the left, this graph never reaches the x-axis. And for that reason, there is an asymptote there. And you know, this has been such a bizarre year for me. I don't even know. I'm losing track of time. Have we talked in this course, I'm mixing together the months and the semesters, have we talked in this course about something called an asymptote? We have. A little, not really, but last year, yes, I think so. It's kind of there in the back of your head. What this is, in this case, is a horizontal line that we draw as a dotted line, and that graph can never reach that line. So what does this function look like? I don't care how well you draw this. It is a curve that looks something like this. And we can put a little arrow on the end there on the left-hand side. So that's what the exponential function looks like. Yeah, I like the way you said that, Aidan. I think we have talked about it in passing, but not officially. We're going to officially talk about it now. So you have a picture of the graph, and now we can write out what the domain is. It's pretty clear that no matter which way you go, left or right, you can always continue to draw the graph. The range, however, is always greater than 0. It gets really close to 0, but it never reaches 0. Because it never reaches 0 vertically, it will never touch the x-axis, which means there is no x-intercept. There's none. The y-intercept is 1, and the horizontal asymptote is the x-axis, which is y equals 0. Any questions with the first example? All right, let's take a look at the second one. The second one has a base of 1/2. So let's figure this out starting at 1. When x is 1, the y coordinate will be 1/2 raised to the 1, which is 1/2. When x is 2, the y coordinate will be 1/2 raised to the 2, which means I square 1/2. If I square 1, I get 1. If I square 2, I get 4. Notice that to go from 1/2 to 1/4, you multiply by 1/2. If we put in 0, this will be 1/2 raised to the 0, which is 1. This will be 1/2 raised to the -1. What does that mean? 1/2 raised to a -1 means 1/2 means 2 over 1 raised to the +1. That's the meaning of a negative exponent. We flip it over. So we end up with 2. We're going to end up with 4, 8. I mean, stop and think. If going this way in steps of 1 for x multiplies by 1/2, then going this way in steps of 1 for x must multiply by 2. Once you get this whole behavior of the function in terms of the base straightened out in your head, it's really easy to graph it. So I'm not even sure right now I want anybody to write anything. I maybe just want you to watch here for a second. When x is 0, y is 1. Since the base is 1/2, every time I go up xy is 1, y gets multiplied by 1/2. So when I go to x equals 1, it's going to be half as great. When I go to x equals 2, it's going to be half as great again. I'm not going to go to x equals 3 because I can't really plot a point in there. It would be, I guess it would be 1/8. It'd be really tiny. In the other direction, if I go backwards 1, x gets doubled. If I go backwards 1 again, x is doubled again. X is doubled again. And of course, we're going to have an asymptote, so you can take time now to sketch this thing. We are still going to have an asymptote on the x-axis, and the graph will look. Don't worry about how well you draw, it doesn't matter. The graph will look something like that. Okay, we have to do the domain. Domain is any real number. Range is still y is greater than or equal, not greater than or equal to, I misspoke. Range is y is greater than 0. No x-intercepts to speak of. The y-intercept is still 1. And the horizontal asymptote is still y equals 0. Any questions with number 2? All right, a quick review here of some things. If the base is bigger than 1, then the graph ends up looking like this. So when you take a look at the graph in example 1, the base was 4. And the graph, when you look from left to right, the graph goes uphill. When you look at the graph for B, 1b, left to right, the graph goes downhill and the base is smaller than 1. So what we conclude is that if the base of y equals c to the x, if the base is bigger than 1, then the function goes up from left to right. Always from left to right. If, on the other hand, the base is a number between 0 and 1, because it can't be negative and it can't be 0 and it can't be 1, then we have a graph that looks like that, which is decreasing. And this ties nicely, and it's a useful idea, into this diagram I asked you to write down earlier. Because now not only can we say the base has to be something indicated by that arrow, but we can put that if the base is in one part of the arrow, it represents an increasing function. If the base is in another part, it represents a decreasing function. All right, we're going to add to that diagram again in a few minutes. What function is this graph? So I want everybody to ask themselves this. What number is y being multiplied by regularly every time x goes up by 1? The question is, if you go from an x coordinate to an x coordinate that's 1 more than the old x coordinate, what does y get multiplied by? And you can go ahead, if you get a response, and type it into the chat, into the message window. Now I will tell you, unfortunately, that the first 3 responses are incorrect. Now the correct responses are coming in. Notice I said when x goes up by 1. Up for x, when x increases, we're going this way, always left to right. So when we go from -2 to -1, y gets multiplied by 1/4. And all that means is this is the function. It's that simple. Okay? So be very careful when you talk about whether that number is 4 or 1/4. 4 would end up looking something like this. Any comments or questions about this example number 2? All right, so now I'm going to introduce 2 more words, and I'm doing all of this today so that it makes our jobs easier later. If you have an increasing function, why do I know this is increasing? Because c is greater than 1. So whenever you have an increasing function, we can call that type of exponential change exponential growth. It's always from left to right. Y is growing. If, on the other hand, in such a function, y increases. So this happens with certain types of investments, population of bacteria, people, the number of people infected with the COVID-19 virus. Those were examples and are examples of exponential growth. If you have a situation where the base is between 0 and 1, we know that is a decreasing function from left to right. We like to use the word or the phrase exponential decay. Radioactive decay that you learn about in Physics 30, and none of you, I don't think, have taken Physics 30 yet. The value of a vehicle, when you first buy a vehicle, every year that goes by it's worth less and less and less. Those are examples of exponential decay. And we can add that now to this diagram, this schematic, which is very useful. I could say that if c is between 0 and 1, that's a decreasing function, or I could say that's an example of exponential decay. If c is greater than 1, we know that's an increasing function. All of these things are from left to right, and that's an example of exponential growth. So a lot of the time when I go over questions, I'm going to be referring to this schematic. I didn't say it, but excuse me, at c equals 0 and c equals 1, there's an empty dot there because c cannot equal 0 or 1. All right, we've got a few more examples to do. The first thing to note, though, is there is a discrepancy here between the textbook and the formula sheet. Okay? The textbook uses c for the base and the formula sheet uses b for the base. We're going to have to get over something here. If the formula sheet uses b for the base in this unit, the formula sheet also uses b for a parameter in transformations, we have to get over the fact that b has a meaning that's indicated by the context of the question. If I said you have y equals cosine of bx, and I say you have y equals b to the x, those two b's mean different things, obviously. The b in the first example is a parameter that results in a change in the period of the graph, or a horizontal stretch, if you like, by a factor of 1 over b. The b in the second equation is what y is being multiplied by regularly, that's as different to the other b as the taste of a pepperoni pizza to the color of the sky. They're just different things. You can't even compare them. So we have to get used to that. Example 3, a radioactive sample of radium. What's Ra-225? It's the type of radium. Has a half-life of 15 days. What that means is that every 15 days, 1/2 decays into a different type of atom. So if you take a look, you start off with this amount, and then one 15-day period later, you have this amount. What has the y variable been multiplied by? Well, 0.5. It's cut in half. And then you go one more increase in x, which is a 15-day interval, and it goes from 0.5 to 0.25. So things are being multiplied by 0.5. Now the questions. What is the initial mass? Well, the initial mass is the mass when t equals 0. Initial means at the beginning. So we're talking about the y-intercept. The initial mass is 1 gram. What value does the mass of radium-225 approach as the time goes on? Well, it turns into 0.5, and then it turns into 0.25, and then 0.125, and then 0.6 something, and then 0.312. Like, it keeps getting smaller. It's approaching 0. And the reason we say it approaches 0 is because there's an asymptote at m equals 0. So the mass as t gets bigger, approaching infinity, the mass approaches 0. It never reaches 0. Unless we're in a physics class where I'll tell you different, okay? But mathematically, it never reaches 0 because of that asymptote. Next question, what are the domain and range? Well, you have to look at the context of the question here. The domain is t is greater than or equal to 0. If this were just an exponential function with x and y, we would probably just say the domain is any real number. But you cannot have a negative time. What is the range? The range is that the mass has to be wedged between but not equal to 0 and possibly equal to 1. It can be this value. It can be any of these values coming down here, but it can never reach 0. So that's the domain and range. Questions with that? Okay, and the last question here, oh, not the last one. Write the exponential decay equation. Well, it's mass equals 0.5 to the t. Because y, which is mass, is changing by being multiplied by 0.5 regularly. Any questions with C? All right. How many days would it take to reach that mass? So if we have mass equals 0.5 raised to the t, then we have to solve this equation. Am I going too fast, too slow, just right? I need to know right now. Okay, that's good enough. Now, unfortunately, everybody, when you look at this equation, you just don't know what to do. You have not been taught how to solve that for y, or for t. So what we are going to do is solve it graphically. We've solved equations graphically now for, well, since grade 10. I'm going to put 0.023, which is a pretty tiny number, for y1, and 0.5 raised to the x. And I'm going to set my window settings up manually to match what we're looking at here. For my x, I would say we can go from 0 to, I don't quite know how far we're going to go to reach a really tiny number of 0.023. Why don't we leave it at 10? If we need to increase it, we can. For my y, I'm going to go from 0 to 1, because that's the range. So when I graph this, it happened quick, but there's that 0.023 which was graphed, and then there's that other exponential function. To find the intersection point, we go to our calculate menu and choose intersect, and go enter, enter, enter. About t equals 5.4422. I have a question for you, though. This is not the answer. It's not the question you have. Oh my goodness. Give me a second. Do you even have this type of question? Let me see. Oh, D is not the question, right? A, B, and C are the question? Okay, so A, B, and C are the same. Do me a favor and cross out on your handout where it says 1/30 of the original. Change it to 0.023 grams. This will just make my life a little bit easier. So in your question, it doesn't say this. It says, how long would it take to decay to 1/30th? Do me a favor and cross out 1/30th and put 0.023 grams. I hate it when that happens. Sorry about that. So does everybody understand? Does anybody have any questions on how I changed the question? Okay. So now the point of intersection of the curve and 0.023 is 5.4422. That's not the answer to the question, though. The question is, how many days would it take? And T is not days. T is 15-day intervals. which means we're going to have to multiply that by 15 to get the true number of days. And starting probably tomorrow, we won't have to do that because we will be a little more sophisticated in our equation. So if I take that x value and I multiply by 15, I get about 82 days. So 82 days is the answer to the question. I apologize for the confusion. In the future, I mean, I'll do my best not to have mistakes, but you know me, I make mistakes. Please, somebody, the first person who notices, go ahead and unmute your mic and interrupt me if there's a problem like that. Any questions with D now? So rounded to the nearest day, it's 82 days. All right, we have one more example, and I think we can do this in about 5 minutes. We have two towns, Allentown and Brementown. I hope it's not lost on you that I'm using A and B to describe the two towns. And the population of Allentown is currently 75,000, and it's decreasing at 5% per year. Annum means annual, which is yearly. Brementown is a population of 10,000 and is increasing at a rate of 9% per annum. And this question is going to teach you how to use an exponential function where the y-intercept is not 1. So when you take a look at the graph for Allentown, we won't worry about what it looks like. What I'm interested in is the fact that Allentown starts off at 75,000. Well, and actually we can sketch in what it's going to look like. It's going to look like this, because the population is decreasing. Brementown starts off at 10,000, and it's going to look like this, because the population is increasing. And we're asked to come up with equations for these population functions. The first thing you need to recognize is that exponential functions normally have a y-intercept of 1. So if I have y equals c to the x, it will cross at 1. The only explanation as to why a different function would have a y-intercept of 2 is that it would have to be 2 multiplied by c to the x. We're talking here about a vertical stretch. And what I'm kind of leading up to, everybody, just want to see something. What I'm kind of leading up to is the fact that we can write some number times c to the x and use the same rules we had for c to the x, except the y-intercept will be a. And what that means is that for Allentown, we are going to have an exponential function that says the population will be 75,000 times some base raised to the t. And for Brementown, we are going to have the population equals 10,000 times some base raised to the t. And this next question, I think it's worthwhile to spend just a couple extra minutes to make sure you get it. If I'm going to start off with Brementown, if Brementown is going up by 9% regularly, then what would we multiply something by to get 9% more? Let's start off with the 10,000. Let's see. If I take 10,000 and I find out what 9% of that is, which is 0.09, and I add it to the 10,000, then I get this number. What do I multiply 10,000 by to get this number? Well, I could work backwards and take this number divided by 10,000. And I discover that the number I multiply by is 1.09. I hope that you understand why it's 1.09. It's 1.09 because if you start off with 100% of something and you add 9% to it, then you're going to have 109%. That's how you increase the value of something by 9%. Can anybody figure out if the population of Allentown is going down by 5% regularly, what base will we have in the exponential function? That means, what is the population being multiplied by regularly? Yeah, 0.95. You're starting off with 100% and you're losing 5. If I told you that I just bought a brand new truck and I'm going to sell it to you with 5% discount on what I paid, then you would be paying 95%. And in decimal form, that's 0.95. So these are the two equations, and we're going to keep coming back to building these application equations in the following units, but those are the two equations. Before we finish this lesson with B, does anybody have any questions about those two equations? All right, B, I believe, is the last question. Yep. And it says, how many complete years of change will it take for the population of Brementown to exceed the population of Allentown? This is Allentown, this is Brementown. We want to know that. We want to know where these two curves are going to cross. So we have to solve this graphically. I'm going to put in for y1 Allentown, which was, I believe, 75,000 times 0.95 raised to the x. For Brementown, I'm going to put in 10,000 times 1.09 raised to the x. I'm going to set up my window settings using my tables, okay? The first thing you need to recognize that if I were to go to my table and start at 0 and go up by 1, I can go to my table and I can see that the population at the beginning of Allentown is 75K and Brementown is 10,000. And as I scroll down, when I get to say 5 years, boy, Brementown still has a ways to go. I mean, Allentown is losing people. Maybe, you know, there's a zombie apocalypse there, or maybe the economy's bad, but people are not sticking around Allentown. On the other hand, something really happy is going on in Brementown, so the population's going up. But man, I could keep scrolling. You know, I could answer this question. Let's do it this way. Let's keep scrolling. At the end of the 14th year, Brementown has not surpassed Allentown, but at the end of the 15th year, Brementown has surpassed Allentown. We didn't even need a graph. It's 15 years. By the way, we didn't need a graph. A is the symbol for years, by the way. Sorry to break it to you. A is a vertical stretch factor. A is the initial population. And A is also the symbol for years. Had the question said to the nearest tenth, then what you would need to do is, I'm going to set my window settings up now and go up to 17 years, because I can see that's where it will be about. And clearly I need to go up to 75,000 to see that first intercept. So here's Allentown. The people are fleeing Allentown. Here comes Brementown. Where do they intersect? They intersect at 14.65 something. Since the question said how many complete years, it has to be a whole number. And by the way, if that intersection point was 14.0001, we would still say the answer is 15. We have to round up in a case like this. Does anybody have any questions with B? Okay, so the official party line is that you have 10 more minutes left in class officially. Of course, you know that my unofficial thought is that if we had 2.5 hours per day in school, that's how long I'm here for to help you with. So there are a few questions for you to ponder and complete dealing with this stuff. And then there's more of that trigonometric equation stuff from the first lesson. I know sometimes it's difficult when we do 2 lessons in one day. It doesn't give you, I don't think, nearly enough time to practice, but we have to deal with it. So I'll unmute my mic, and I've got some things to do here. I'm going to try to get your next assignment in your folders by tomorrow morning. Please don't expect your last assignment to be marked before the weekend. I don't know if it's going to happen. If it does, great, but if not, that's fine. If you need help, let me know.